So, good morning, ladies and gentlemen. I just checked the floor is empty, so maybe we can continue with our program. And it is my great pleasure to introduce to you Benedetto Nastasi. He is an associated professor and senior energy planner at Department of Industrial Engineering at Tor Vergata University of Rome. He got the PhD title with honors from Sapienza University of Rome, with a dissertation in energy systems planning and design. The core of his thesis was published in Energy and became one of the most cited papers in 2016. He was rewarded as a best senior researcher at Smart Energy Systems Conference in 2018, the best young investigator in Hydrogen Technology Conference 2022, and previous affiliations include the Technical University of Eindhoven in the Netherlands, International Solar Energy Society, and Guglielmo Marconi University in Italy. He is Deputy Editor-in-Chief of Transformative Energy and Editor at Energy, International Journal of Hydrogen Energy, Renewable Energy, Applied Energy, and his work spans across scales and domains in energy planning with a profound knowledge of the built environment. He authored more than 100 publications with an H-index in Scopus of 41. So please give a warm welcome to Benedetto.
Thank you very much. Thank you for inviting me. So what I'm going to talk today, I'm going to talk about quite complex issue. So how the built environment is usually dealt with in the energy planning. And this is quite, let me say, complicated if it starts. Yes, okay. Just to start who I am, Benedetto Nastasi, Ingo already gave me a very nice introduction. Thanks for that. And the involvement on many SVA journal. And he already said something about me. I wanted to highlight my journey in the SDEWES conferences. So I started exactly 10 years ago. It was a nice start, getting the Best Poster Award and then the most cited paper. And today I'm plenary speaker, so I'm very honored to do this. So let's go to the point. The real issue with built environment is that building scientists and energy planner do not talk too much. So I try to fill this gap, considering the different challenges according to the different scales that analyzing the built environment will lead to. First of all, the main difference is if it's a new built environment or existing one. And if we think about Europe and China, so this is already a big difference. And then all the scales you should take into account, because each scales require different skills and expertise to analyze the problem. Brief agenda. So the title was cross-domain and multi-scale. So I will also go not really in an order when I will talk about it, because there are these effect on each scale to the subsequent one and to the previous one to account for the energy issue and the role played by built environment in the energy planning. So we will see example of the different scales, but we need to understand first what is the context and why is required this cross-field skills to analyze this problem. Mainly domains, thanks all the collaboration. So is my invited speech, but of course, without all the peers where I have been working with, there will be possible to be here across 4 official domains. So means building physics, energy storage, energy system, energy analytics, where we can identify actually topics that more or less I try to summarize as just cross-domain, but of course each topic will affect all the other one in a different percentage, let's see. Okay, what is the context? So the Main gap is that energy modelers see, for instance, the next 10 years scenario with energy retrofitting as a energy saving finally in the results. While from a building science perspective, you can save energy, reducing the operation, but you need to improve the performance. And there are different KPI. If they are KPI talking about energy use, so you need to reduce, and what you see in the second figure. But contemporary, you should comply with new standards. So the standards and the requirement are evolving. So it means that contemporary, if we look at an energy perspective, is like you contemporary have an increase of demand and increase of production. So, and finding the best way to do this match is always challenging. And we cannot forget what is the real application. So here you see there are three different business models that usually characterize the energy performance contracts that are, let's say, the business effect or whatever you do in the built environment. So it means that if among these three actors, the client, the energy service company, and the bank, who is going really to check what is the saving generally that you produce with your intervention. And if the saving is core business for more than one actor, of course, each one will try to push harder to get it. But of course, this is different from usual citizens. They just allow the energy service company to take over the expenses, and then they will do something. I will maybe pay less my energy bill, unless is someone that in the built environment has also a core business. So let's talk about building portfolio companies. So part of the core business is also managing effectively the built environment. And I will go through a few steps in an incremental way during this presentation, keeping also how the collaboration finally were delivered to the society, because the outreach of all this activity is the main core of my research activity. I started with other colleagues to understand what were the main factors in energy planning and how we can go, especially in the different kind of resolution if you would like to solve a problem. And first one that is quite clear for the building scientist, less maybe for some energy system people, maybe for energy planner is clear also, is that you need to check what kind of resolution you need your analysis. And when we are talking about buildings, so you cannot go further than hourly resolution. So if you say something about annual demand, annual consumption of a building, you don't say anything. So we need to start speaking the same language. That means we need to analyze same resolution of models. Secondly, depending on resolution on other fields, you have to see if the data you have are currently able to be used immediately, or you need to pre-process this data. And finally, the first gap we identify in energy planning is that when we talk about sector coupling, we consider transport a sector. So many models look at transport as a separated sector, but buildings do not have yet this importance. Let's talk about the context. So without any detail that maybe can be neglected for people that are not working in the building science. So, but first of all, buildings is mainly weather-dependent energy user, plus an occupant-driven energy users. So that means that even in a country like Italy, so a small country compared to China, the differences you have in climate inputs, if you want to see it from an energy modeler perspective, is changing a lot through the location where is located your building. Why is important this? Because it's important because the value of the buildings depend on the energy label, and the energy label is not anymore a fixed value. As you see in the table, the building belongs to a class depending on a percentage of the performance of a reference building where each value, each building envelope, for instance, thermophysical properties, depends on the year of construction, and because we need to comply with the decarbonization goals, and decarbonization pathway means you need to take into account also the carbon budget, not only that you want to reach zero in 2050 or 2060. It means that each buildings, each 3 years, there is an update of the limit value, and your building must deal with this new value every 3 years. So retrofitting is almost something that you cannot escape from anymore. So even if you do a very nice energy retrofitting today, it's not said that you will keep this class in 10 years. So this is completely a paradigm shift. And if we look at the European directive, they fix also a limit year, 2035, where you cannot sell properties with a class less than C. So if you cannot sell, the property doesn't have any value. That is quite strong. And that's why it's an important issue in energy planning. And then if we go generally to energy modeling, but for building scientists, quite important, our imagination is to solve this issue, no? The performance gap. So you design a building, you imagine, let's say, you predict how it's going to behave, but finally, it's only operation that would say something to you. And operation is also part how the energy system is going to behave, and eventually, if you get or not the targets you set when you design the scenarios. So I'm going now across the scales, not in this order. Try also to guide this journey, starting from an example that maybe most of you already experienced it. So I had the pleasure to be one of the co-chair of the SDEWES conference in Rome. And in the social event, there was the visit to Galleria Borghese. So Galleria Borghese is a very important building, is preserved not only for its architectural appearance, so not only the exterior walls, but also inside. So inside this, maybe one of the most beautiful buildings ever built, and is also hosting a very complicated thermophysical problem that is the museum. So you cannot touch anything, theoretically, but also in some way, this building has to comply with the Energy Performance Directive. How? That's the challenge. So the first really nice challenge between energy and architecture was how to make it as efficient as possible. So that means that we located all the new HVAC system that were not in the original design of more than 400 years ago as part of the spaces that were already used for the natural ventilation. So where you see the fireplaces, we put the terminals of the HVAC plant, where you see the way to extract the exhausted air that was driven naturally by natural ventilation. We put the extraction unit. And where you see the technical rooms that were used mainly as a kind of room of cold air to then later be delivered through the building using all the cavity you see, not only fireplaces, but also you see between pavement and ceiling. So the idea finally was to deal with this challenge, but keeping the energy issue in a solvable way without touching the buildings. So why I make this extreme example? To say that we can solve even if the most challenging environment, but we need to take into account all these features when we try to talk about the building stock behavior at national level. So when we go to urban scale, that's much different. So it happens to me in many conferences of energy planning that the building issue was maybe preliminary solved, just saying, okay, just replace every heating supply with heat pump. Let's put 3.5 COP, and then we have the total heating demand to be solved in the supply. Okay, from a building perspective, that's not possible. What we can do is, of course, distinguish among the urban building portfolio, what are the different levels of heating. That means that generally you have user that can be distinguished in high temperature, medium temperature, low temperature, compared to what in building science is this level of temperature. That means 90 degrees for gas boiler, 55 to 65, maybe condensing boiler or air-to-air heat pump. Oh, sorry, a gas heat pump, or low temperature when you can deliver heat at 35 degrees, or maybe with the new buildings, even lower, even almost to ambient temperature. So it means that each user is to be identified for his electricity and heating demand, but this is not possible. It means that you should run millions of simulation if your portfolio is made by millions of buildings. So what you do generally is to leave the electricity part for how is composed now the built environment. So this is an assumption that maybe in 10 years we need to change, where when the electrification of buildings will be a relevant part. So this maybe is applicable still for most of the European countries, but maybe with some developing countries that are already switching to fully electrified buildings is an assumption to be carefully taken into account. But that means that each temperature needs a conversion system that is able to comply with this temperature. And the heating system, the terminals, were designed for this difference of temperature. So you cannot replace a gas boiler with a heat pump without accounting that each terminal in each room was designed for a different temperature of 60 degrees between the 80 degrees of the boiler and the 20 that you want to keep in the room. And you know, we cannot, we don't have to call the Fourier formula, but if we reduce the delta T, so the difference temperature, we need to enlarge the surface. So that means that your terminals must be double maybe, unless we reduce also the heating demand. And that's why we need to make efficient the built environment. The other important stuff that depending on how is made the built environment, how is located in the urban city, how is the texture of the urban, means that from an energy perspective, you have a different ratio between the power and the heat demand. And that means that the more power you have, the more you can directly integrate renewables. The less you have, unless you electrify this heating demand, that would be challenging. So what we went through was to analyze 3 different contexts, Rome, Berlin, and Copenhagen, in terms of built environment, and see the differences in the scale of red of the high, medium, and low temperature share among the demand, and how, if we want to see at urban level the increase of renewable, what will be the effect on the primary energy. But this is not touching the building. You are just doing something on the energy supply, so on the conversion part. So it means that usually, I use this picture, but we can use the scheme when you present energy plan or H2S. You have all these combination, but still there is this missing point that maybe is classified in other use, like the buildings. What does it mean? That in an area of power to watt, so what to do with buildings? So it means that you start from this possible scenario. And at the beginning, we had interesting discussion in Italy. You know, Italy has a very high share of gas as based of thermopower generation, thermoelectric generation, sorry, and also the use. So 91% of buildings are heated with a gas boiler. So the challenge was talking about the blending as a way to push people from the gas sector to say, okay, you say that it's feasible, do it in an indirect way to, let's say, push for the development of electrolyzers. And we start to thinking, okay, let's check if they want to support this, what will be the result? So how to integrate the power to gas. That generally means that you can increase the direct renewable heat of a small percentage that is limited to what? To the energy supply that is a high temperature. So the idea of gas sector is to still have combustion. And then, okay, let's see the effect and then compare with power to heat and the combined power to heat and power to gas. Nothing to say, that means that we need to switch from the normal fossil fuel-based supply. So if you see each level, CHP for high temperature, gas heat pump for medium temperature, to electrified one that could be a transcritical heat pump to reach the same temperature, or two-stage heat pump for the 65 degrees. But this has to be done gradually, cannot be just, okay, let's switch. And that already allows some gain. So you see at increasing the renewable share, what will be actually the fraction of energy that you can cover with renewables. But still limited. If you do just power to it, you have still a lot of fossil-based or fossil-derived heating supply. So the idea, okay, let's merge. Let's do contemporary power to heat and power to gas. In the transition scenario, okay, you reach more than the sum of the previous two operation. I know already what would be the observation or the comment on this. Okay, but heating with hydrogen is crazy. Yes, but we are not talking about heating directly with hydrogen. We are pushing gas people to say, okay, let's integrate it, because the idea was at that time, let's create the demand for electrolyzer to lower their price as they are developed, and then we switch. This is crucial because we can have other kind of effect that usually are forgotten in energy planning, that maybe even the terminals are part of the things that you cannot change. But of course, these are extreme examples that I wanted to show just to increase the complexity of the problem. But then we see what will be the modeling issue and how we try to come to a solution. And the other one, that is usually you talk about energy retrofitting, considering fixed values, but all the phenomena are dynamics. That means even the conductivity of the building envelope is changing his behavior with the temperature the building is subject to. So it means that, as you can see in this previous one, you model something, already the model is wrong, and the model can help you to finally, when you compare with the measured data, to select the best material, compare and accounting for the climate condition. So there is no way to say, this is the best material, this is the best insulation we can use, whatever the climate is. And this is another important issue. From a modeling perspective, you see the cycle at the bottom of this slide. From a building science perspective, you start descripting the building and do all the elements, so it's a bottom-up approach. But this is not typical from energy modeling. Energy modeling use buildings more as a top-down. Okay, what are the consumption? Maybe we can somehow make up what will be the energy profile, because now buildings are important because are the main prosumers. They are the one that can locally produce energy, they can use energy. I need to know this, otherwise I cannot do demand response, I cannot create business models. And here we come with the first interesting result. Rather than thinking just to energy efficiency, let's switch to rational use of energy. What does it mean? That the energy retrofitting you do is not measured on how much energy you can save, but how the demand profile will change and how it will be able to be used in a flexibility market. So maybe your building is going to consume more than the most efficient intervention, but it can trade more energy, and the effect on the system will be much better. So it means that when you have a built environment that is mostly built in the 20 years after the Second World War, you have to still deal with this high, medium, and low temperature heating. You cannot just say, okay, let's do heat pump. But that means that when you are going to change something, you can see in the bottom how certain strategies of electrification can change completely the frequency of the flexible load, increase it, and put it as an actor in the flexibility market. Maybe this one is going to give you, in terms of energy simulation at national level, much more savings than just reduce the demand of the building itself. Now, something that maybe is more interesting for our Chinese colleagues. So with a nice collaboration with Sichuan University, we studied what's going on the off-grid and grid-connected buildings in China. So that means that you should comply with some comfort temperature that you need to ensure, otherwise building scientists are not doing their job. And that means that you have changes. You see the blue, the red, and the yellow dots, where you, for instance, electrify the different services and how can change the demand also, accounting from the short, medium, and long-term scenarios. That means how the weather, since, as I said, building is a weather-dependent, occupancy-driven energy user, how the climate change will affect this way to behave. And what is interesting is what you see in the comparison of this graph, that the same month projected in 2030 and 2050 at the bottom will require a different strategy and a different installation of renewables because something will change. So it means that resiliency of the built environment in terms of energy load has to be taken into account in the future scenarios. What can change for the grid-connected buildings? First of all, you don't have so many constraints, no? In the off-grid, you need your building with most probably a very large renewable production locally, while you can use the grid as backup, as the way to balance what you locally are producing. But the interesting part is that while from a building perspective, you are modeling so many loads, so the energy demand will be quite complicated. What is really useful at energy planning is what finally is the strategy to optimize this building portfolio. What does it mean, actually? That the study we carried out for 4 different conditions in China, so Harbin, Beijing, Chengdu, and Xiamen, will change, affect also what we define the carbon payback. So you are doing intervention of the built environment. They cause the increase of the embodied carbon emission of the buildings. So when the savings of this carbon emission will balance this investment. And this is quite useful if you want to do the future scenarios, accounting for the transition pathway. You cannot now say just, okay, in 2050, we will have 0 carbon emission. Okay, how to reach it? And that's the way. So we need to do intervention that take into account also your carbon budget and has to be tailored on the built environment. That means that when you have your Pareto front of solution, accounting for the minimum and the maximum, because you need to consider an interval of embodied carbon emission, it will change the results. And as you can see quite clearly in terms of investment, if you compare the different climates. I mean, if you have the maximum carbon, the embodied carbon emission, it can happen that you do your retrofitting. The retrofitting is very expensive, but finally you erase your carbon budget available for the sector. If you see the case in Xiamen, no? You have many gray dots that will be much more emitting and also much more expensive. So why to go to that? The problem is sometimes we go there because we don't do the calculation of the carbon or the embodied carbon emission for the built environment. So you think it's the cheaper solution from an energy perspective, saving energy, but then finally you are erasing more carbon budget. So the carbon payback will be longer than the date of your final scenario. This is interesting because you make many assumptions on how the aspects of occupancy driven in terms of energy use, but it changed a lot when happened the COVID-19 lockdown. And it changed not just temporary, but also structurally. So after the COVID-19 lockdown, smart working became structural because not just a phase. So what does it mean? That you design a building, you imagine a load profile, you verify the load profile once the building is built. Okay, you maybe were wrong of 20%, and in building scientists, 20% is very nice. If you look at the ASHRAE, so the American Society of Heating, Refrigeration, and Ventilation, and they say, oh, wow, you got, but it's 20% far from the real result. Oh, you were so good. This is nothing to say in energy planning, no? 20% is too much. Plus, you finally change all the assumption because the load profile that you try to predict it were completely changed on the way we use the building. So roughly, you can see in the same period how it changed the complete profile of those electrified building. And that means that you would like to account for this performance as demand to trade in demand response of flexibility market, then you have an issue. So briefly for this, you have the green dots on the here, quite stable, these green dots before COVID. And after COVID lockdown, you have much more peaks. And this is not exactly maybe what you like, unless these peaks are in the same phase of the renewable production. If they are faced with solar PV, nice. That's rational use of energy, it's not efficiency. So you are on time matching, and that it works in terms of balance, okay? That means very nice for energy community framework. And then it change when you account for the different use. Something changed completely if the buildings was already fully electrified. Because you read the differences I showed before, if you have a component for heating and cooling that is driven by another system, that is not maybe trading with the electricity market. But when the building is fully electrified, you have contemporary, you should have one function that is accounting contemporary for occupancy-driven, weather-dependent factors, the two main forces for the built environment energy use. And then you see the heat maps. We are talking about three completely different kind of building. It's the same building, fully electrified, same almost 11-month period in 2018, 2020, and 2021. But in terms of energy balance, in terms of energy market, completely three different users. The energy models look at this, and you can guess that they are three different buildings, but from a building envelope perspective, from a system perspective, they are still always the same. The difference how it was used energy, because they change a lot the occupancy. We are going through the scales. It means that while you are planning, the national energy scenario, you talk about thermoelectric power generation, also 1,000 of megawatts. Here we are talking about 1,000 or million of small components. Like this one is the open data analyzed for the heating generator, so mainly gas boiler, in the north of Italy. So we are talking about 4 million gas boilers. And the funny thing, when you try to do prediction, to make a prediction or to use other data for the energy purposes, like, okay, when those components were installed, because maybe you can try to couple the nominal efficiency to the heating system. If the gas boiler was installed in 2000, then it would be most probably more efficient than the one installed in the 90s. Okay, but then you go to the data and you found strange things like, I don't know, 30% of the heat generator were installed in January, in the middle of the season. Well, a little bit strange. You think maybe they were not working properly and the owner was obliged to switch. Or what happened in 2000? Why double of the trend was the new installation? There was some incentive, no? You start thinking about all these things. No. The fact is, most databases that were created in a quite following a rush rather than in an emergency situation rather than properly, what happens? The heat generator doesn't have a clear year. Okay, let's put it 2000. We don't know the month, because one of the things to be controlled by the environmental protection authorities, when you install it, after exactly 2 years, you need to control the emission. We don't know the date. Okay, let's put 1st of January. If we go granularity of this analysis, it's like the 1st of January, rather than celebrate the first day of the year, all people were installing gas boilers. But it seems an extreme example, but this is the kind of data you are dealing with. While the first case, the Galleria Borghese, you say, okay, this is one of the few buildings compared to the building stock worldwide. Here we are talking that many databases that are input for energy modelers, they are affected of these strange things. If you don't know the phenomena, then there is something complicated to explain in terms of results. We are coming to the conclusion. Each component then must be done also at system level. So if you are still within the building itself, or an apartment or building complex, and the heating was for a while the only field where an objective function of efficiency must be done and measured, it means that you try to combine system. So, and what you would like to do is to give professional maps, like engineering in the 70s, where you can combine the systems to immediately understand what is the efficiency of the system. Okay, I combine a CHP and a heat pump. Okay, what will be finally, the thermal efficiency of this system to understand if it's better or not of a single component or what are the sides. The other issue, this cannot be done univocally because as you can see on the right, if you have one user or you have 10 users, means one order of magnitude of heating use, you have quite different profile of system efficiency compared to what? To the thermal load of the system. So if the system is running 100% of nominal load, that will be an efficiency. If not another one, also the trends are different. So still accounting for the weather-dependent force in the built environment. That is not properly taken into account in energy planning generally. So this is a pre-process that you all ask to the building scientists, but has to be finally done as a pre-processing for the data. This journey almost conclude to the district scale because we are focusing a lot on district when there is this quite vague definition depending of the kind of sources that you would like to integrate. So the district case now is raising a lot of importance for the cooling, especially when now the new building are data centers. So what does it mean? That you are rather than looking at the generation, you are looking at the use, analyzing what will be maybe the baseline, the base load, that will be the data center, because you cannot interrupt this operation because there is a business behind it, and there are services that must be delivered. But you can play maybe with people. They would like to switch on or switch off some devices in the house. So they want to discharge the battery of the electric vehicle and so on. So first things comes to consider all these parameters that still have to do something with the buildings for their use and how to switch. And specifically in this study, as you can see from the two heat maps, how you can optimize also the master planning and the optimal dispatch. So basically, rather than buy 15 machine and the associated capex, you buy less and you use more. So you see how ordered is the use and the production of cold energy when you can play with different elements like cold energy storage. That is something that usually you don't consider at national level. So what about your insertion of district cooling in your future scenario at national level? Almost nothing. Already district heating in some country, like in Italy, is still a very small amount of contribution on the total energy demand, on the total energy supply. Finally, why we do all this? We do all this for the outreach of this research. The policymaker is not aware if you use TEMOA, H2RES, energy plan, times, they see results. So that means that it's crucial to be able to compare results from different frameworks, different models, different inputs when you provide something. Okay, it's clear that built environment is still missing here, so we need to work a lot of this because the focus is clearly on economy and energy outputs to do this comparison. So I'm concluding the speech with these 4 open research questions. In many cases, at national level, it seems obvious the answer, while it is not at the built environment. Like, okay, are going to electrify everything, or there is just a fuel exchange? Would be possible for buildings to produce a kind of fuel and to exchange it with the networks. When we are going to install some distributed generation, we will change the supply, we do something hybridized. This hybridization should be accounted in the transition pathway related scenario. And energy retrofitting maybe as a different value. Is not an energy efficiency measure for the buildings. maybe it's an energy efficiency measure for the system. That means you can still consume more, but if you consume exactly on time, then you are solving, the equation of the balance hourly, or something that I didn't say because it was a very recent reform. All the electricity market now, they don't have hourly resolution. They have 15 minutes resolution. And this is completely changing also the approach. So we were using to have the simplification, to say, okay, if we talk about watt hour, or okay, just watt, okay, in 1 hour is the same number. Let's do it in 15 minutes. And to be sensitive as engineers, to the numbers and say, okay, this order of magnitude is fine or not? At 15 minutes is quite challenging. And finally, of course, we cannot ignore data. That means would be possible, rather than data-driven, to have a data-aware planning. So where data, where you know where they come from, how, they can actually be the tool to solve the issue. Thank you for your attention.
Benedetto, also for keeping excellently in time. So now we have quite plenty of time for asking and answering questions. Neves always have a question, but and as you are the only one having a question, you will be the first.
Thank you. Just for warming up other participants, I'm a little bit perplexed that I didn't hear explicitly anything about storage. And we energy planners see buildings inherently as a huge storage potential, cheap one, because we are talking about heat, hot water, cold, electric batteries in cars that could be used to balance power system, but also integrated power system in the building.
Okay, so from this aspect, I didn't show anything because actually I was a little bit scared to go too much in detail in the building science. What I mean is this one. When we talk about storage in buildings, so first of all, thermal mass. So using the thermal inertia of the building. But for an energy planner, this is more like, okay, what will be finally the load profile of those heating or cooling system that I can translate in eventually gas supply or hopefully electricity demand at national level to face with the renewables. So there are the issue in accounting for the thermal inertia of buildings can be done properly for the new buildings. For the existing one is still very complicated. So you can account some kind of reduction of the real demand, but the issue is comfort is not controlled in existing building. That means the building officially is providing a service. This service is not measured. So you measure just CO2, if you are lucky, or temperature. You don't measure humidity or other kind of lighting visual performance that are the core business of the building. So they are accounting the new one because the new one received certification and it's like a degree, you get points and credits. You are a platinum building, okay? That means that this certification is making sure this performance, so the value on the market is higher. And that works a lot. But in context where the existing building are 90%, it's difficult to, it's better like in a conservative way to avoid thermal inertia. For other kind of storage, let me say that they make sense at district level. And that this is something that you actually integrate, but you do not couple often the building with the storage. You account the user is not a building, it's a load for you. So it's not like you are talking with the building guys, you are talking about one of the load of your system. I try to put more in a building perspective. There is, you must account for, but it seems that it's an energy engineering problem, not a building one. So that's why like building people are a little bit step back on this. But sure,
Yeah, you want to?
Well, energy engineers are already putting buffers, usually 200 liters. But why not 1 cubic meter or 4 cubic meters? Depends on the space you have.
Yes.
And the main mechanism how to govern that will be tariffs.
Yes.
So if it's cheaper to store your heat or cold into water, then store it into the grid, your solar power, you will maybe do it. So different tariffing. It is working. Yeah, it is working. Okay. Okay. Also, what did I want to say now? Tariffs.
Yes.
Tariffs are going to be governed that.
Yeah.
This is the main mechanism. So we are going to be seeing buildings actually playing on the markets through the tariffs, not something, but everything. Have coupling of wholesale market tariffs prices with retail market prices. This is something that you can already do in some countries in Europe. I'm not sure about Italy.
About Italy, quite complicated. Let me give to the audience my personal example. So I'm doing this since 15 years. So I finally bought a house, very long mortgage. We had few money to do the energy retrofit. Okay, we put in class B because then you have more efficient house. When we went for thermal storage is going to occupy at least 2.5 square meter. That means that if you buy a house between 3 and 4K per square meter, you are wasting, let me say from a citizen perspective, this 10K. Okay, maybe 10K is what you have available. Plus the fact that you are dealing with this thermal storage with a centralized heat pump that is going to cost in Italy around between 12 to 13K. There was already a new heating system we kept. We are using most the split for thermal and cooling, but there is a clear issue that is not a building problem. The ratio between the price of electricity and gas in Italy is very aligned to the ratio of the performance of those systems. So if it's OPEX wise, then okay, why you don't do electricity? If it's CAPEX wise, that's a problem. Because you have 20K for your retrofitting, so you are not going to buy the furniture because you need to buy this heat pump to do everything. Most probably you are not going to do unless there is a tariff incentive. But then let me say this is something not building scientists. It's for sure policymakers. So we need to provide scenarios to say if we electrify, if we do this, we get this advantage. But from a building perspective, okay, I live. I mean, it's not my detailed interaction with energy modelers. That will be with policymaker, and then it's another position. For you, yes.
Ravi is pressing on time. We should save some time, but there is still space for question. You should take advantage of Benedetto's expertise. Yes, Peter.
It's Peter Varbanov from Széchenyi István University in Hungary. I've been following your rise through prominence in SDEWES, but I'm impressed by this energy community direction. In this sense, we had previously a joint project which involved a refinery close to Genoa, and it's in the town of Busala. And we were supposed from that project to transfer some heat from the refinery to the town. But when it came to implementation, something from the legislation cut this off. So how do you see this interaction on building energy communities in Italy How does it go? How realistic it is? Or do we need changes in legislation and regulations?
Something that was done recently and can most probably will have a very huge impact. It is that you can participate in a national energy community. So we started with the limitation of the single electrical substation. So all the people that are connected to this substation can exchange energy because energy was a good, there were taxes. So until the Renewable Energy Directive 3, so that in Italy was implemented starting from 2022, but finally it went officially, it was officially adopted in 2024. So in 2 years, we have these provisional laws. We had many constraints. They are erasing some constraints. So that means if it's a national energy community, you can exchange virtually with whatever you want, whatever aligns with your load profile in terms both of load or eventually production. That means that you are changing and erasing also the permitting issue. Okay, I cannot do, yes, for it is not possible, but at least for electricity, you can do it. If you create many national energy community, you are accounting, of course, for the losses eventually in transmission and distribution, but you can overcome let's see. I mean, yes. And that I think will be a game changer, especially now with the electricity market at 15 minutes resolution. That will be those one who are more advanced in acquiring, recording their data of use. That's something that usually is just the distributors that will do. Now you can feel active in, I want this data. The data is available, you should request. You should download this data. But they are there. So that's maybe an empowering action.
I also have a final question for you. You said the high percentage that you are heating in Italy with natural gas boilers. So I think we have almost the same situation in our countries. And we discuss a lot, how do we make the transition, maybe towards mainly electrically driven heat pumps? Apart from any problems with heat pumps, what are doing with our natural gas grids? When they get used less and less, the costs for the grid for the individual users or per kilowatt hours increasing and increasing. And finally, we close a part, but there's still 2 or 3 houses there using gas. Do you have a plan in Italy to face those very practical problems?
They started, okay, all this issue usually works if you do something in economics, no? So the first thing was done 1st of January 2025, when they say, having any energy retrofitting you do in Italy for your own house is then they say fiscal deducted in 10 years. So you spent 100K, then for the next 10 years, you will receive half in 10 annual rates. Means you will get out of 100K, 50K, 5K each year back from the fiscal system. They exclude the gas boiler as this intervention. So if you buy a gas boiler, you cannot deduct the tax for the 50%. But there are also other ways, no? You make the company, your construction company, buy the boiler and make you on your account as a further works, and then you can deduct the amount in any case. There is something, some discussion still on phasing out on many systems. There are leading cities that are doing this because they or belong to Climate Neutral Cities Alliance or in their SECAP, so Sustainable Energy and Climate Action Plans, they inserted this. So, but always indirectly. You want to control the emission locally for the emission allocation as a city, because you want to maybe be in the rank of the most level cities, and then you do something denying specific use of fuels in the heating system. So that's the case.
So let's thank Benedetto once more for his presentation.